Hey everybody, Chris McClure here. I, this is actually the second recording of this lecture today. I just finished about a 55-minute recording, but the audio did not record. This same thing happened a couple of lectures ago, and I don't know what's going on. I'll have to report this issue to systems integration when I get back from my trip. But so we're going to go through this again here. Sorry you didn't see the first one, but it wouldn't have been as interesting, well, who knows, as the first one because there was no audio. But hey, you could see my face and hopefully you can hear me speaking and we'll kind of get through this. All right. What we're talking about here in section 3.3 has to do with examining certain properties of functions. Folks, throughout the rest of our time together with college algebra, as well as for the rest of your time in trigonometry and calculus, we're going to be studying functions primarily. There might be some topics from, say, geometry and stuff, but by and large, 98% of your time from here on out in studying mathematics will involve functions. Okay, so the first topic, though, we're going to talk about is what it means for a function to be even or odd or maybe none of the above. So your function is going to fall into one of those three categories. It's either going to be even or odd or none. Now, algebraically, we can determine that a function is even when you replace x by negative x, and you end up getting the same thing after you go through and algebraically simplify that functional expression. Does this look familiar? Remember when we were looking at the graphs of expressions and what it meant for the graph to be symmetric about, say, the y-axis? If you replaced x by negative x and you got the same expression, that meant that the graph was symmetric about the y-axis. So same thing here. And hey, folks, for those of you going on to calculus, this is very important. And besides, very handy as well. So an even function, if you have the point with coordinates x comma y on the graph, then also negative x comma y is also going to be on the graph as well. So if it's going to be over on the one side of the y-axis, you'll have the mirror image over on the other side. And an odd function is a function going to be where if you replace x by negative x, you get the negative of the function. And again, if you remember the discussion that we had regarding symmetry of graphs, if you replace x by negative x and you get the negative of the original expression, that means that the graph is going to be symmetric with respect to the origin. Okay, so if x comma y is on the graph, then negative x comma negative y is also on the graph. That's what it means for the graph to be symmetric with respect to the origin. So this theorem basically says again what I just told you regarding symmetry of the graphs of these functions. Symmetry with respect to the y-axis for the even function, and symmetry with respect to the origin for the odd function. Here's a nice picture of what we're talking about here. This first graph is the graph of an even function. If you were to take a look at the y-axis and then take a pair of scissors on a piece of paper and cut out this graph and then fold the picture right down the y-axis and fold that picture in half, you would see a mirror image of that graph on either side. Okay? Now, this graph here in the middle is neither symmetric with respect to the x-axis or the y-axis or the z-axis. There's no symmetry, so that means that this graph could not possibly be the graph of an odd or even function. Now, this third graph over here on the right has symmetry with respect to the origin. So that means that this is the graph of an odd function. If you were to take the line y equals negative x that comes down diagonal like this, and then rotate and fold, you would have mirror images of each other for the graph. All right, now if we, instead of just seeing the graph, we only saw the equations, we could tell whether the equation, or the function I should say, is odd or even. Just replace x by negative x and see what happens. For this first function right here, f of x equals x cubed plus 5x, just replace x by negative x. And let's see what you've got. And indeed, when you do that, replace x by negative x, you end up with, after you factor out the negative there, you get the negative of the original function. Remember, the original function was x cubed plus 5x, and you get the negative of that function. So you get f of negative x being equal to negative of f of x. So what does that tell you about this function? X cubed plus 5x. Is it odd? Is it even? Or neither? Well, because f of negative x is equal to negative f of x, that means that this function is an odd function. Let's move on to the second function and replace x by negative x. Now, when you have negative x squared, that gives you just x squared again. So you end up with just the same function. You have g of negative x is equal to g of x. That means the function is, drum roll, even function. All right, and then what about this last function? Replace x by negative x, and you end up with, now negative x cubed is negative of x cubed, and you get negative 4 times negative x cubed, which is 4x cubed, plus 1. Which is not the same as the original function, and it's not the negative of the original function. So what does that tell you? That means that this function, negative 4x cubed plus 1, is neither even nor odd. Okay? All right, moving along here. Let's talk about what it means for a function to be increasing or decreasing or constant over some interval on the x-axis. Now here's kind of a play function here. It's a function, the graph of a function at least. Now, if you were to be in a little car, generally traveling from left to right, or if this were a map, maybe a cross section of the road that you're traveling on, going from left to right, generally speaking. If you're on this little car, you would be going downhill as you went from left to right along the curve until you hit here. Then you would be going uphill, uphill until you get here, and then you have flat surface, constant elevation here, until you hit this point here at x equals 3, and then you go downhill again, where your altitude is decreasing. Well, you think about altitude as function value, then you could easily see that you could talk about where the function is decreasing or increasing or is constant just by looking at where is the graph losing altitude or picking up altitude or staying the same over some intervals. All right. So let's talk about first, where's the function increasing? Well, it's going to be on this interval. You see where I've highlighted in red? So that's going to be between -2 and 0 on the x-axis, from -2 to 0. Okay? Excuse me, -4 I should say, because this is -4 right here. So this is -4 all the way to 0. So on the interval from -4 to 0, the function is increasing in value. Or which you could also express on this open interval. Let me just say this, and I'll say it once, is when we're talking about the intervals in which the function is increasing or decreasing or constant, make sure that you express them as open intervals, because at -4 and at 0, at neither one of those points is the function doing anything as far as increasing or decreasing or being staying the same. So you will express these intervals of doing something as just open intervals. Okay. The function is decreasing in value, both right here on this interval from -6 to -4, and also on the interval from x equals what, 3 to 6, from +3 to +6. So on those two intervals, the function is decreasing in value. And it's actually going to be constant on this interval here from 0 to 3. 0 to 3. Function is going to be increasing. Here's the algebraic definition. Function is increasing, so if you pick any two values of x on that interval where we're saying that the function is increasing, let's say suppose x sub 1 and x sub 2 or any 2 points, and let's just assume that x sub 1 is less than or to the left of x sub 2. Then in order for function f to be increasing, then we say that f of x sub 1 is less than f of x sub 2. And then similar discussion for your function f decreasing in value. If x sub 1 is less than x sub 2, then you'd have f of x sub 1 greater than f of x sub 2. Let me show you a picture here after we talk about your function being constant. Basically, for any two values of x, f of x1 is the same as f of x2. Okay, here's kind of a picture. Suppose that you've got x sub 1 and x sub 2, and x sub 1 is to the left of x sub 2. But for the function to be increasing, we say that f of x sub 1 is less than f of x sub 2. So if you were to make a little line segment connecting this point to this point right here, that line segment would have a positive slope. Similar discussion for your decreasing function. You have x sub 1, x sub 2, and your f of x sub 1 is greater than f of x sub 2. Think about temperature. If your temperature is decreasing with time, and you have time 0 here and time 1 there, well, your temperature at time 0 would be higher than that at time 1, for example. Anyway, and then here's your constant function where your functional value is the same for all values of x on the interval. Okay? Now let's talk about what it means for a function to have a maximum or minimum value. Now, maxima, as you see right here, is not only the name of a model of Nissan, which I happen to like. I someday hope to own a Maxima, but regardless, maxima in this case means multiple of maximum. And likewise, the singular version of minima is minimum, right? So then you have several of minimums, it's really minima. When we talk about local maxima, we're talking about two or more little places where the function has a maximum value. And where we have local minima, it's going to be where places where your function has these localized minimum values. All right, so here's kind of a picture of a local maximum value. It could also be a global or absolute maximum value, but this certainly qualifies for a local maximum value. So, of course, you could tell from the graph, it's easy to find the top of the hill, so to speak, right? But mathematically, we say that your function has a maximum value at x equals c, and that maximum value is whatever f of c is. And also notice to the left of c, your function is increasing in value until it tops out. And then to the right of x equals c, the function is decreasing in value. So for any value of x not equal to c, so any value of x to the right of c or to the left of c, f of x would be less than f of c. Okay, so there's a nice little definition of what it means to have a local maximum. And likewise, for a local minimum, we say that there is a local minimum at x equals c with that minimum value of f of c when you have some neighborhood of values surrounding c with x values such that f of x is greater than or equal to f of c. And to the left of f of c, the function is decreasing, and to the right of c, the function is increasing in value. Okay? Moving along here. So here are the algebraic definitions to have a local maximum and local minimum values. Just a repeat of what I just said is that we say that the function f has a local maximum at x equals c when there's some open interval I. And we actually happen to like to use the letter I to represent our intervals. Now, so for example, if we say that the local maximum happens at x equals 2, then we can have some open interval, say from -1 to 4 or whatever. As long as c is somewhere in that open interval. So we can make that open interval small or as large as we want. But as long as there's some open interval, such that for every x value within the open interval, the functional values would be less than or equal to that local maximum. That's really what this is saying right here. And kind of the same discussion here for the local minimum, except all the functional values will be greater than or equal to your local minimum value at x equals c. Okay, so try not to let this algebraic language scare you. Just try to verbalize it in a way that makes sense to you. Okay? Here's a picture of a function right here. And notice with the little arrows that go up here and there, that to the left and to the right, the function will go up and increase to become arbitrarily large. So we're only really focused on this region, say from about -3 to +4 or 5 or something on the x-axis here. So are there any local minimum or local maximum values? So they're easy to pick out. There's a local minimum value there, a local minimum value there, and a local maximum value there. So you need to answer the question, at what numbers, if any, does the function f have a local maximum? Well, at x equals 1, there's a local maximum of 2. Okay? So there's local maximum at x equals 1. There it is right here. And that maximum value is 2. You might see similar questions on the My Math Lab homework. All right, where are the local minimum values? Well, at x equals -1 and also at x equals 3. And what are those minimum values? Well, f of -1 is 1 and f of 3 is 0. So your answer would be 1 and 0 for those two minimum values. Okay, where is the function increasing? Well, from here to here and also from here to here. So in other words, on the interval from -1 to +1, and also on the interval from 3 to as x goes to +infinity. So on those two intervals, so -1 to 1 and from 3 to infinity, those are the two intervals in which the function is increasing. The function is decreasing over here to the left and also over here to from 1 to 3. So those two purple regions. So from -infinity all the way to -2, actually to -1 I should say, and also from 1 to 3, as you see right there. Okay, here we go. Absolute maximum, absolute minimum values. In some textbooks they'll call these global extreme values, right? Global minimum, global maximum, absolute minimum, absolute maximum, all the same thing. Basically means the absolute largest value or smallest value that the function is going to ever achieve over its domain, or some closed interval which you specify. So basically, let me just summarize what these definitions mean. Suppose that we have some function f over some interval I. I could be negative to positive infinity, could be from 0 to 1 or negative 3 to 5 or whatever. And in fact, I doesn't even have to be some closed or open interval. It could be half open, half closed, or whatever, over some interval on the x-axis. Now, in order for us to have an absolute maximum value, all other values of the function have to be less than or equal to that maximum value. So suppose that we say that absolute maximum of the function occurs at x equals u. Then f of x is less than or equal to f of u for all other values of x. Remember, f of u is what we're calling the absolute value the absolute maximum value of f. And similar discussion for the absolute minimum. If we're saying that the absolute smallest value of the function on the interval I is going to be happening at whatever x equals v is, then f of v is that absolute minimum value. And that f of x is going to be greater than or equal to f of v for any other values of x on the interval I. So let's now put this discussion in practice here. Suppose that we've got the graph of some function on the interval from 0 to 5. What is the absolute maximum value? The absolute maximum value is going to be right here. That's going to happen at 3, and f of 3 is 6. So that absolute maximum value is going to be 6 at x equals 3. And notice that any other functional value is going to be less than or equal to 6. In this particular case, any other values of the function is going to be less than 6. So for all x on the interval from 0 to 5, f of x is less than f of 3. And likewise for the minimum value of x on this interval, of f I should say, that's going to happen at x equals 0. That minimum value is 1, and any other functional value is going to be greater than 1. How about this function right here? Now this trick question, if I were to ask the question, what's the absolute minimum value? And the answer is there isn't any. Because if you see this little hole right here, that means that the function's not defined at x equals 3. Now, if the function was defined there, and it was really whatever this is right here, as you go from left to right in order for this curve to be smooth, then one would be that minimum value. But because the function is not defined there, then there is no minimum value. If I were to ask you the question, what is the smallest number greater than 0? What would be your response? The answer is there aren't any. Okay, same discussion here. By the way, at x equals 5, we have the absolute maximum value of this function at of 3. Okay, the function is going to be less than 3 for all other values of x from on the domain from 1 to 5. So you'd answer the question, for what x value is there an absolute maximum? That x value is at 5. What is that absolute maximum? It's 3. There is no absolute minimum value because of that hole at x equals 3. Now, what's going on here at this point right here? Well, you could say that there's a local minimum there, but it's I'm sorry, it's a local maximum there at this point right here, but it's not an absolute maximum, nor is it an absolute minimum either. Nothing's going on as far as extreme value goes there. All right, how about this graph right here? This graph, some function with the domain from 0 to 5, the range that goes from 1 to 4. Now, we could easily pick out the absolute maximum value at 5, 4. Okay, no problem there. But what about the minimum value? For what x value does that? Well, there's no 1x value. It's going to be on the interval from x equals 1 to x equals 2. That you're going to have a minimum value of 1. Okay? So one of the takeaways that you have here is that you could have extreme values that happen at multiple values of x. And not only that, you could have these extreme values happen along intervals. Okay? Moving along here. Is there a maximum value for this function here? Well, here's a clue. Notice the little arrowhead. This little arrowhead basically means that the curve just keeps on going, and it doesn't stop. As x increases, y increases. And so that means as x goes to infinity, y goes to infinity. So there's no maximum value. But there is a minimum value that's going to happen right down here at 0, 0. Okay? How about this function here? Do you see a maximum value? And the answer is no, because again, as x approaches 5 from the left, the function is going to just go on up to positive infinity. So there's no absolute maximum value. Is there an absolute minimum value? No, because of the fact that there's a hole right here at x equals 2. So here's an example where you have a function that has no absolute max and no absolute minimum value. It happens from time to time. So not all continuous functions will have absolute maximum or minimum values on just any arbitrary interval. But we are guaranteed, though, if you do have a continuous function over some closed interval, then we are guaranteed that there will be an absolute maximum and absolute minimum value on that closed interval. Here, this is important. First of all, what is a continuous function? Well, a continuous function, without getting too technical, for those of you going on to Calculus 1, you're going to explore this in a lot more detail, but let me just kind of sketch the outlines here. An extreme, in order for us to have this extreme value, it's important for us to have this condition of a continuous function. Continuous function basically means that, well, if you were to take a pencil on a piece of paper and sketch out the graph of a function over that closed interval from A to B, that you would not have to lift your pencil at all. You just make one single stroke to draw the graph of that function. There aren't any holes, there aren't any jumps, anything like that. Now you could have like a jagged edge, a jagged point where the function changes direction all of a sudden. As long as every point is connected, then you have a continuous function. Very important concept, what it means for a function to be continuous. And also the closed interval. The interval needs to be closed. If the interval is not closed, and you have at least one endpoint not included, then you could have a situation, let's go back to the previous slide, you could have this situation, right here, where the function goes on up to some, brand of infinity, like here. So on the interval from 3 to 5, for example, you see at 3 the function's not defined, At 5, the function goes on to become arbitrarily large. But if we were to say on the interval from 3.5 to 4.5, including those two endpoints, then that function really would be continuous. So we need these two conditions, continuity and closed interval. Provided that we have those two conditions, then we are guaranteed that there is going to be an absolute maximum and absolute minimum value. Now, I like to visualize stuff. I'm a very visual person. And one way that I could help you visualize this is just on a table, flat surface, just get a piece of string. And, suppose that your table has, is relatively narrow. I've got this little table right here that is maybe about 2.5 feet wide, about yay big if you can see it. And then imagine if you were to take this string and just, it'll give you some slack in between your fingertips. Maybe you got 3 or 4 feet of string. And then just drape that string between one edge of the table to the next. And I guarantee you that that string could either go straight across, in which it's constant, in which case you'll have an extreme value that's the same for minimum and maximum. Otherwise, your string is going to do something like this, or it just might go bow down like this, or it might have several ups and downs. But there's going to be at least one maximum value and one minimum value. So how do you do it? You just go through and find all the local minimum values, as well as at the endpoints, as well as all the local minimum values as well. And then once you've found the values of all the local extreme values, as well as the endpoints, then you pick the largest value and the smallest value. And you will have found the absolute maximum value and the absolute minimum value on a closed interval. And that's pretty much all I'm going to say on that, except for the fact that understand that you could have a nice continuous function that's defined everywhere. You could have a domain that includes all real numbers, or at least some interval that's much larger than what's indicated by a comma b. But all we're saying here, though, is that on any closed interval, whether that closed interval is from, I don't know, from -1/8 to 1/4, or -1,000,000 to +1,000,000 closed. No matter the size of that closed interval, as long as the function is continuously defined over that closed interval, that function will have an absolute maximum and absolute minimum value on that closed interval. Guaranteed. All right. Now, here's where you get to pull out your graphing calculator, and I'll show you on your TI-80 whatever calculator how to graph a function and find its maximum and minimum values, at least a local max and local minimum. Okay, so pull out your graphing calculator, and we're going to put in this function right here, 2x cubed minus 3x plus 1. Okay, plug in this function, and then on the viewing window, let your x minimum be -2 and your x maximum be +2. Now, I did this from start to finish on my previous recording, so you'll see all this stuff already loaded up. So in the equation editor, here's that function right here, 2x cubed minus 3x plus 1. Go ahead and plug that function in there, and then go to your viewing window, where it says window right there, and let x go from -2 to +2 with x scale at 1/2 maybe, and let your y minimum be, say, -3, y max be +3, and a scaling factor of 1 maybe. and then hit graph, and here's what the graph looks like. And then we talked about how you can find the coordinates of your local minimum and local maximum values. Here's your local maximum value. Let's do that one first. Now you can start off by hitting your trace button, and then use your left arrow button to move your little spider, so to speak, I call it a spider, to get close to that extreme value that you're interested in. So make your spider go to the top of the mountain there. And then you can see, okay, somewhere in the neighborhood of negative 0.68 for x, and the y maximum would be somewhere around 2.4 or so. Now, if you want an exact value for x and exact value for y, then what you could do is you can go, you see the little calculate menu? You have to hit the second button and then hit this trace button in order to access your calculate menu. And then select your maximum function, which is number 4. Okay, now it's going to ask you for a left bound, as in left bound on the x-axis. So we had already estimated at negative 0.68. So we can choose some x value to the left. Like, how about negative 0.7, for example? So negative 0.7 is some number to the left. You could have just as well chosen negative 1, whatever. And to the right, how about negative 0.6? Negative 0.6. Enter. And then guess, how about some number in between? How about negative 0.68, for example, as the x-coordinate? And then your calculator will quickly come up with the x-coordinate. It looks like it's very close to negative 0.7, huh? For the x-coordinate. And the y-coordinate, there it is. It's very precise. Y equals 2.4139997. That is the local maximum value here. We could also have the same discussion for that local minimum value. We go back into our calculate menu and select the minimum function. Now, here we could be a lot more generous. Here we can say, okay, left endpoint, say 0, right endpoint of, say, 1.5. So let's do that. So left endpoint of 0, right endpoint over here, call it 1.5, 1.5 input, and then let's just choose, say, I don't know, 0.7 or something for our guess. That'll get us pretty close. And then there are a couple of different techniques that a calculator uses to find extreme values of functions, which you'll learn when you get to calculus. But whatever method it uses, it'll come up with the x and y coordinates for that local minimum value. And that local minimum value is about negative 0.414236 at this x coordinate here, 0.70710689. Okay, so now you know how to find the x and y coordinates for your local maximum and local minimum values using your graphing calculator. All right, now let's talk about average rate of change of a function. Average rate. What is average rate of change? Can you think of anything that involves rate of change? Well, we're surrounded by change, and that's what calculus is all about. Not that this is a calculus class, but I understand that a lot of you are headed to calculus someday, so I will not shy away from certain preliminary topics of calculus anyway. But anyway, rate of change basically means the rate at which some uh, quantity changes. Like, for example, at some time the temperature was 75 degrees. Excuse me. And at some later time, the temperature was maybe 68 degrees. So if I want to calculate the average rate of change of that temperature, all I would need to do is just figure out, you know, what is the change of that temperature with relation to the amount of time that passed. Now, I could, at any given time, use a computer with the appropriate sensing equipment, calculate the instantaneous rate of change of the temperature. You could have like a gust of cool air that comes in, and all of a sudden that rate of change is very rapid, very high magnitude in the negative direction. But maybe there's a gust of hot air that comes in, and maybe that rate of change is now rapid in the positive direction. But if it stays relatively constant, then you won't see that rate of change being much beyond zero. So the instantaneous rate of change might fluctuate on a moment by moment basis, okay? But the average rate of change, all I want to know, okay, maybe the temperature changed 7 degrees over 3 minutes. So 7 divided by 3, or -7 over 3, or whatever that is, that's your average rate of change. Okay, well, let me also point out that you can figure out your average rate of change by, for example, running. Suppose that you run 1 mile over some distance, right? Maybe you start off with a nice smooth track, and then you go through some gravel, and then you go over some rough field. Maybe you have to jump over some logs and big rocks or whatever, and then you go through a field again and back on the road and whatever. So as you go through those different legs of the journey, your speed's going to change. But to calculate your average rate of change, is all you need to do is to calculate, the distance that you traveled, which is 1 mile, divided by the time that it took you. That's it. 1 mile divided by however many minutes it took you. So it could have taken you, say, 9 minutes to do 1 mile. So you've got a rate of change, or an average speed of 1 mile, or actually 1/9, I should say, 1/9 mile per minute, because it was 1 mile over 9 minutes. Not to say that that was the speed that you were going the whole time. That was just your average speed. So let's do yet another thought experiment. Suppose that you are driving down some freeway or highway, and with a speed limit of, say, 60 miles per hour, just to keep it simple. 60 miles per hour is the speed limit. Now, suppose that law enforcement were to use radar to clock your speed at 60 miles per hour at point A. And then point B, 1 mile down the road, suppose that another law enforcement officer clocks your speed at 60 miles per hour. Now remember, this distance separating those 2 points, A and B, is 1 mile. But what if, for some reason, they really wanted to check you out, because maybe you have a history of speeding or whatever, but hey, they clocked you at doing the right speeds at both endpoints, but you managed to get through there in, say, 52 seconds. In which case your average speed was a lot higher than 60 miles per hour, because you did 1 mile in less than 60 seconds. Okay, everybody see what's going on? So, hey, that's how you could use the average rate of change. And when you get to calculus, you'll see how we can say with certainty that at some point in that journey between point A and point B and your highway, that your speed would have had to have been greater than 60. Okay? All right. It's called the intermediate value function, but we'll talk about that in some other class. All right, so let's talk about how to find the average rate of change of a function. It really comes down to calculating the difference in the value of the function over the difference in the independent coordinates. So whether we're talking about how temperature changes with time or distance changes with time or whatever, it's going to be basically the delta of the function, in other words, delta y, over the delta of the independent variable x, delta y over delta x. If you were to use a line segment connecting those 2 points on that function's graph, then the slope of that line segment would really be that average rate of change. So all you really need to do to calculate average rate of change is evaluate your function at the endpoints of that time interval, or x interval, divided by the length of that x interval. So let's do an example here. Suppose that we got the function 3x squared. Here's a graph of 3x squared right here, starting off at x equals 0 and going to the right. We could go to the left, but it would just going back up again in the opposite direction. Well, it would still be going up, but as x goes to the left. All right, so first of all, on the interval from x equals 1 to x equals 3, we see that the function increases from 3 to 27. But what is the average rate of change of this function on the interval from x equals 1 to x equals 3? Well, the short answer is delta y over delta x. Here's delta y over delta x. So, in other words, f of 3 minus f of 1 divided by 3 minus 1. But f of 3 is 27. See, 27 right there. Minus f of 1, which is 3. Which is 24. 27 minus 3 is 24, divided by 3 minus 1, which is 2. 24 over 2 is 12. So 12 is the average rate of change of the function between these 2 points in time, or x. So once you understand how to do this, you can calculate rate of change between any 2 values of x. All right, so between 1 and 5, so it'll be between this point here and this point there. Hey, f of 5 minus f of 1 over 5 minus 1. You know what to do. Plug in the numbers. F of 5 is 75. F of 1 is 3. 75 minus 3 is 72. Divided by 5 minus 1, which is 4. 72 divided by 4 is 18. So 18 is going to be the average rate of change. Now, notice that this rate of change, 18, is larger than the rate of change between 1 and 3. And that shouldn't be a surprise. As you look at this graph, you look at the line segment that could connect this point here and this point here versus the line segment that would connect to the 1, 3, and 575. It's the second pair of points that would have the steeper line segment, the larger slope. And in fact, if you were to take a line segment from 1, 3 to 7, 147, that line segment would even be steeper. That rate of change between x equals 1 and x equals 7 would be even higher. We can calculate that. And there it is. F of 7 is 147 minus f of 1, which is 3. You get 144 divided by delta x, which is 6. You get a rate of change of 24. So yet a higher slope, a higher rate of change. Now let's talk about secant line. A secant line is nothing more than a line that goes through 2 points on a curve. the curve being the graph of a function. All right, so the blue curve is the graph of some function, f of x. And we've got two values of x equals c and x equals x. And you have these two values of y, f of c and f of x. So what is the slope of that secant line? Well, it's going to be your average rate of change of the function between those 2 points, your delta y over delta x. So you see m subsecant, that means the slope of the secant line. The average rate of the change of the function between those 2 points. So that's what we're saying in the yellow box here is the average rate of the function over that interval from a to b is going to be the slope of the secant line going through those 2 points, a comma f of a and b comma f of b on the graph. So let's go ahead and take a look at what would be the average rate of change of this function between two values of x. I don't know, let those two values of x be, say, -2 and +1. Well, to do part A here, remember, let's do delta y over delta x. So here's your, f of 1 minus, in fact, it's not f, it's g. G of 1 minus g of -2. That's what you've got going on here. Divided by 1 minus -2. Now, g of 1 minus g of -2, whatever that works out to be, that whole thing works out to be 18. Divided by 3 is 6. So that's the slope of the secant line, because that's the average rate of change. So find an equation now of the line going through those 2 points. In other words, find an equation of the secant line. So use your point slope form. Here's your y minus y sub 1 is equal to the slope times x minus x sub 1. You got your slope. That's going to be 6. And your x sub 1, y sub 1 are coordinates of some point. So you could use either this point here or this point right here. And in particular, let's use -2, I should say, and g of -2. Now, g of -2 is apparently -19. So you plug in those numbers, simplify, and it works out that y equals 6x minus 7 is the slope-intercept form of the equation of the line that goes through those 2 points. And then if we wanted to, we could graph both the original function, g, as well as the secant line, which I'll let you do on your own. You know how to graph functions now. You can plug in -2x squared plus 4x minus 3 for y sub 1 in the equation editor of your graphing calculator. And you can plug in a y sub 2 equals 6x minus 7 and plot both of them on the same axes. You can plug in a -4 and +3 as your x min and x max. And you plug in -25 and +2 for your y minimum and y maximum. And see what you get. Make sure that you use appropriate x scale and y scale. And you can see that this line, y equals 6x minus 7, intersects the graph of g, this g right here, at this point here and this point here. And now, focusing on the graph of g first, you notice that the graph of g is fairly steep right here, steeper than the line. But as you go from left to right, the steepness becomes less and less steep, and that instantaneous slope of the curve becomes more and more shallow until it gets pretty much 0 when you hit x equals 1. So the rate of change for the function itself changes over time on the interval from -2 to 1. But the overall average rate of change is 6. Okay? All right, so that's it for when we were talking about properties of functions. So we talked about evenness and oddness, And we talked about what it means to find a maximum minimum value. We talked about how to determine over which intervals a function's increasing and decreasing. Regarding extreme values, what it means to have a local maximum and local minimum value compared to global or absolute maximum and absolute minimum. Okay, and not all functions have absolute maximum or absolute minimum values. You could have a function that where you see the graph keeps on going up and up and up without end, so it's going to be going and rising ever higher and higher, but without end. But you can't say that there's a maximum value for such a function. It's like asking you, what is the largest integer? And the answer is there isn't one. Because whatever integer that you name, I would just add 1 to it, and then we would have yet a larger integer. All right, so when we get into the next section, we're going to talk about our library of functions and mathematical models. It'll be a fairly short section, and but I'll save that for tomorrow. I don't want to go through this too fast. And but how you can do some mathematical modeling using some functions. And then, actually, that's 3.6. Sorry about that. 3.5, we're going to be talking about transformations. Now, when we're talking about transformations, we're going to be talking about how you can manipulate the arguments as well as adding or subtracting things from the original function in order to shift the graph up, down, left, right. Maybe you can flip the graph with respect to a line or axis, and that sort of thing. So we'll talk about transformations tomorrow on Monday. Then on Tuesday, we'll talk about transformations, no, not transformations, but mathematical modeling, I should say, on Tuesday. And then so on Tuesday, after I get done talking about mathematical modeling, because that's a real short section, then I'll put up a Chapter 3 quiz and then start Chapter 4, where we'll be talking about linear and quadratic functions, which is a really important discussion because a lot of what we do in algebra involves those two types of functions, linear and quadratic functions. Okay, so that's it for today, and we'll talk with you next time.